Hi guys, Vince here. Today we're going to get into using Fusion 360 adaptive clearing with desktop machines. Specifically, how to get good feeds and speeds and what to look for while machining. We'll do test cuts with both high and low axial depths of cut to show you the differences and benefits of each one. We'll go over basic machine setup, router, and tooling. And hopefully I can show you some tips and tricks and things I've learned along the way. Hope you guys enjoy. For those of you that didn't watch the Tormach XS Tech Teen-Up video, I should probably introduce myself and give you a little bit of background. I was recently hired by Saunders Machine Works to work with Proven Cut on the desktop machine side. And that's where we come up with cut recipes that are reliable, efficient, and repeatable for specific materials in every machine. My first CNC was a Shapeoko just like this. Although I didn't have a nice fixture plate or mod vices, a probe, or a tool length offset sensor. It didn't take long to really try and push the limits on the Shapeoko. Basically, if I could fit it on the machine, I wanted to cut it. Right now I'm going to show you one of my favorite parts. It's actually one of two assemblies. And this is a sheet metal press die. And what you do is you put a piece of sheet metal in there under a hydraulic press, tens of thousands of pounds later, and out pops this just perfect part. A die like this really couldn't be machined without a toolpath like Fusion 360 adaptive clearing. Alright guys, enough about me. Let's get back to the adaptive cutting. The first thing I'd like to point out is that all these end mills are name brand. We have 2L, Amana, Datron, Helical, Lakeshore Carbide, and Destiny. There are lots of other manufacturers out there as well, but these are just some of the tools that I've used over the years with good results on desktop machines cutting aluminum. These end mills are arranged by Flute Count, so let's go over why Flute Count matters. But first, let's talk about chipload. I like to use a minimum chipload of 1 thou. All these manufacturers do have recommendations for the chiploads that you should run their tools at, but you'll find pretty quickly that in a desktop machine, it's pretty hard to hit those recommendations and still get a good quality cut without chatter. A minimum chipload helps ensure a reliable cut where the tool isn't rubbing and the chip is sufficiently thick enough to manage the heat. So chipload is the amount per tooth per revolution that's cut. So the more flutes you have, the faster you're going to have to feed for that same RPM to maintain that chipload. Let's say we program a single flute to 40 inches per minute. At that same RPM, we're going to have to run this 3 flute 3 times as fast, 120 inches per minute to maintain that chipload. Also, this 3 flute is going to take quite a bit more power because it's taking 3 times the amount of material per revolution. Also, the more flutes you have, the less chip space you're going to have for chip evacuation. Now, that's huge when cutting dry. Basically, single flutes, I love cutting dry. They're almost uncloggable. You can full width slot, no problem. Something like a 3 flute cutting dry, you're pretty much going to baby the machine, especially if you have closed geometry where you don't have space to get rid of all those chips. I recommend that if you are going to run 2 or 3 flutes, that you do have at least an air blast or some type of lubrication. I've used a WD-40 drip can before, but they can be very messy and WD-40 just goes everywhere. And I've also used a cheap Amazon mister, which has worked pretty well, but I don't really like to have an air compressor running all the time. I found that this minimum chip load is pretty universal with the exception of micro tooling. So once you get to about 1/16 of an inch and under, definitely run the manufacturer's recommendations because at that point, power and rigidity really isn't a problem. So the manufacturer is going to know best how to run that tool. But for 1/8 inch, 1/4 inch, 3/8, you stick with this and it's kind of hard to go wrong to start out with. Let's take a look at some of the single flutes we have on the table. We have a diamond coated 2L, a ZRN coated Amana, and an uncoated Datron 4-in-1 6mm. These 2 end mills right here are what I'd like to call, regular duty, pretty much a general end mill. They are lower cost, especially compared to the Datron, but they don't like to run at the same RPM. I generally like to run both of these under 20,000 RPM because they aren't especially balanced, and any kind of vibration will end up to some degree in the cut. I haven't noticed a difference between the diamond coating and the ZRN, but it does give peace of mind, so why not? The Datron is specially balanced because it's actually designed for machines that have a much higher RPM range than our desktop machines. And it also features a wiper flat on the bottom, and that lets you get a pretty good floor finish, especially compared to most single flutes, which aren't really known for a good floor finish. Also, the Datron is pretty much my pick when I want to remove a lot of metal and I don't mind running some RPM. So I usually run this one, anywhere from 25 to 30,000 RPM, no problem. Dry cutting as well. So today we are going to pick the Datron, mainly because I want to spin it faster, I want to take a bigger chip, and I want to spend as little time machining as possible. So let's pick the one we can run the fastest. Let's talk a little bit about the setup. I am running white steel core belts, although now Shapeokos come with black fiberglass core. The steel core is about 20% stiffer, but it didn't fatigue very well, so you usually only get, it's a limited lifespan, 6 months to about a year, which is not bad for me. I think it's worth that 20%. We're also running a Saunders Machine Works fixture plate with the stiffener rails, and on this project, because our stock is so big, 5" by 16 by 0.5, running 2 sets of mod vices, just so that there's enough clamping on the part, that we don't get any kind of unwanted vibrations because of overhang. With the new setup, the first thing we're going to have to do is tram in the fixed side of these mod vices. And what I like to use when having an aluminum fixture plate and vices is the bit 0 LED to tell me when I'm actually making contact. That'll get you within about a thou, and that's plenty good for this type of machine. Let's talk a little bit about the spindle we'll be using on this machine. As you can see, it's a Makita Router. This is model XTR01Z, but stock they come battery powered, and that's not going to work very well with CNC operations, so it has been converted to DC power supply usage, so I could just plug it in. The stock speed controller has been converted to a Vesc, and these are used mainly for electric skateboards or electric bikes or do-it-yourself one-wheel type of things. It gives me complete control over the Makita and lets me pump a little bit more power into it while seeing real-time data and letting me log everything for a view after the cut. It is overvolted right now to 27 volts, and my RPM range is 2,000 to 38,000 RPM. One of the things I really like about these Makita routers is you can run up to a 3/8 or 8mm end mill. That's a Destiny Diamondback, and this is an 8mm Datron 4-in-1. These are some of my favorite ones to run. Single flutes run super well at high RPM, high balance, and I don't know, they just cut like magic. Now let's talk about why adaptive clearing is such an efficient roughing strategy and how it differs from traditional pocketing. The magic behind adaptive is its constant cutting load. By keeping its step over very controlled, called the optimal load, it eliminates spikes in tool engagement and allows you to run much more aggressively. It also gives you the option of running much higher axial depths of cut. In comparison, here's a traditional pocketing tool path with the same step over as the adaptive. As you can tell, the tool engagement radically changes in the corners due to part geometry. And this definitely means you'll have chatter and you'll have to reduce your feed and speeds accordingly. Okay, let's draw up the test part real quick so we can make those test cuts for the high and the low depth and some of the older cuts that I thought were good but ended up not being that great. I want to create a sketch. We will make a center rectangle, and it is a 4 by 6.5. Let's dimension it. Okay, finish the sketch. We're going to extrude it 1.5 inches tall. Now we want to create those slots for the adaptive, so we'll create another sketch on the top, and we'll do a 2-point rectangle this time. Okay, I want these to be about 1.5 inches wide, and I want 3 of them, so I'm going to make a rectangular pattern. I'll choose all the lines and then just pull it out. Looks good. Finish the sketch. Okay, so I want to extrude these down about 1/4 of an inch just because I just want to show you guys the differences between these. We have some real cutting to do later on a nice part. So there you go, looks good. Now time to put in some cam. All right, now here's where I'm gonna cheat a little bit. I've already spent quite a bit of time with proven cut recipes figuring out what to run on this tool on this machine as far as step overs and step downs. So what I'm gonna do is just copy that tool path, go into my new part, I'll paste it in my setup, hit OK, edit, pick my new geometry right here. There you go, nice shallow adaptive toolpath. Let's go to the feeds and speeds real quick. 25,000 RPM, 75 inches a minute, 3 thou feed per tooth, optimum load of 0.23. So that's almost 100% step over. And I've found that with these Datron end mills, you can almost run like a high feed end mill, just a shallow depth of cut, fast, and they leave a beautiful finish, make some really nice chips. Roughing step down, 30 thou. And because I'm cutting over 50% of the diameter, this feed per tooth is true. There is no chip thinning that we have to worry about. All right, let's go get the deep toolpath, copy paste. Okay, edit this. We're going to apply it to our new geometry. There you go. Nice deep toolpath. And so these two toolpaths are actually the same material removal rate, but as you can tell, there are going to be quite a few differences between both of them. Let's look at the feeds and speeds of this one. The same, 25,000 RPM, cutting feed rate 50 inches per minute, feed per tooth of 2 thou. Now we will have an optimum load of 40 thou and a maximum roughing step down of 250 thou. And what this means, because this is under 50% of our diameter, this is not actually our feed per tooth, that we have to factor in chip thinning. So our true feed per tooth is around 1.5 thou, which is above my minimum chip load, so it'll cut fine, no problem. For our third slot, we're going to try some feeds and speeds that I used for a long time and ones that I thought were pretty good, but ever since I really started looking at the data and doing the proven cut stuff, I realized that I definitely could have cut a lot faster, a lot harder, and saved myself quite a bit of time. What we're going to do is we're going to duplicate this deep depth of cut, edit it a little bit. I used around the same parameters, the same spindle RPM, the same feed rates, the same optimal load, but my maximum step down was only 100 thou. So we're going to make it just one pass, so minus 2.1. All right. And then we're actually going to pick the correct geometry this time. Okay. So there you go. What's interesting is I thought I was doing really good with this toolpath. You know, everyone runs adaptive at first and they want to cut as deep as possible. But the problem with that is the deeper you cut, the more axial force you put on your machine, and pretty much the more rigid and more powerful machine you're going to need. It's all tied together. So this is only 100 thou depth of cut. And the MRR, the metal or material removal rate, was 0.2 cubes, whereas both of these were 0.5. And that's quite a difference. And I really wish I had run some toolpaths like these because just the amount of time it would have saved. The first cut we're going to make is the shallow adaptive pass. And I'll stop halfway and pause the machine just to up the feed override so you can see how it's going to act a little bit more aggressively. Cut sounded great, really nice, even and consistent. Even with 50% override halfway through, it performed really well. Floor finish is nice, reflection's nice. Even though adaptive's not a finishing strategy, it doesn't hurt. I really like this kind of chip shape. It's a nice, soft little curl. They don't interlock and they're not sharp, which can be important if you machine at home or you don't have an enclosure or something like that. The next cut will be the high depth adaptive. We'll be cutting a little bit deeper than 1D, which in my opinion is about the limit for most desktop machines unless they have linear rails or they've been modified to be a little bit more rigid, or they have a spindle and they have more power. I know everybody wants to cut full depth, but when you have to make your radial depth of cut so small, there's a certain point where you're just probability of rubbing and things going bad just goes up way too much for it to be worth it. Does look cool on Instagram though, not gonna lie. Totally different sounding, right? Louder, and you could definitely hear peakier tones. There's also evidence of chatter when it enters and exits the cut. Floor finish, not as great, but that's always going to be the issue when you have a high amount of step overs. Chips look nice and shiny, very consistent, not sharp at all, so that's good. But compared to that first cut, it just didn't sound like the end mill was having a good time. The walls, there's some chatter, the floor, there's some chatter. Anytime that end mill is bouncing around, it usually means it's gonna not last as long. So, first cut, second cut, same material removal rate. Which one did you pick? I'd go for the first one, every time. The third cut is the old recipe, so let's see how it does compared to those first two. Yes, it is a little bit deeper than our first cut, a little over 3 times as deep, but we're going to take the same radial step over as our second cut. I do predict that it will sound better. Chips will still look good, the cut will look a little bit better than the second one, but the numbers will tell you that the actual material removal rate is just not worth it. It's less than half of this first one. But let's get cutting and I'll let you guys see the difference. Okay, well that didn't sound as bad as that second cut. Chips look pretty good, nice, shiny, but there was still a little bit of evidence of chatter in the cut. You could hear a little bit, and even when I bumped the feed override to 200%, it still didn't match the same material removal rate as that first cut. So is using that extra flute length really worth it? Maybe if you cut a whole lot and you want to, pinch every penny, but I really haven't seen a drop in tool life when using the shallow adaptive type strategies. Usually I will drop an end mill and break it, or I'll crash it and it's my fault before a tool ever wear out. I actually don't think I've ever really worn out a tool.
Okay, so we've gone over the low and high depth adaptive cuts. We've seen the differences of the sound, finish, and feel of each one. Now it's time to get in depth on how we came up with those feeds and speeds. I started off using a workbook that estimates machine force, tool deflection, and spindle power usage. These factors are important because those are a desktop machine's biggest limitations. Recently I've been using a program called Millilyzer. It's a machining simulation software that can predict milling forces and tool deflection as a function of workpiece material and machining parameters. It can plot the development of the forces acting on the tool during one full revolution. Let's look at the force plots for those first two adaptive test cuts. On the left is the low axial high radial, and on the right is the high axial low radial. Both of these cuts are at the same SFM and very close in MRR. Here's where it gets really interesting though. The peak and average forces are much higher with the high depth adaptive cut. It's easy to tell that our shallow cut is a much better option for this tool in this material with my machine force parameters. Our test cuts back up this data as well. Now let's apply that shallow adaptive proven cut recipe to a real part. This is a custom intake manifold plenum floor with raised velocity stacks. There is quite a bit of material to remove, so we're going to run it just a little bit more aggressively. First thing we're going to do is open up the Millilyzer, and I'm going to keep the same depth of cut and width of cut. However, I'm going to increase the spindle speed to 30,000 RPM, which is the maximum RPM for Makita Router. I'm also going to increase the chipload to 5,000. So you can still see, really nice looking graph here. Peaks aren't bad. My peak feed is under 18 pounds, which is my Shapeoko force limit. Peak axial is pretty low, and wattage is still pretty low, under 300 watts. Tip displacement looks good, tool stress looks good. The material removal rate is a little bit over 1 cubic inch per minute, and while I know that doesn't sound like much, you have to realize this machine weighs under 100 pounds and we're using a router and belts and plastic V-wheels, so in my opinion, it's pretty respectable, especially if it's a nice quality cut without chatter.
If you're a beginner or a noob with aluminum, one of the most important things to check before cutting is the mechanical condition of your machine. Belts should be properly tensioned, V-wheels should be adjusted until they don't spin by hand, the router or spindle should be trammed in, and a calibration test like a circle, square, diamond should be done to ensure accuracy. Once you feel confident in your machine, install a tool that you don't mind possibly destroying and do your cam. Start out with slower RPM so feeds will be more manageable. And if using Fusion 360, one of the most important things to do is check the simulation before starting a cut. This will save you potential headaches from collisions and crashing. Listen to your machine. If it doesn't sound right, it's probably not right. Inspect your tool before cutting with a loupe or microscope to ensure all the cutting surfaces are in good condition. A small chip on the leading edge can make or break your project. Spend time dialing in your work holding. If you can't hold your part, you can't cut your part. A setup like an SMW fixture plate and mod vise make this easy, but if you have an MDF table, you might have to get a little bit more creative. And last but not least, don't be afraid to go easy at first. You can start with lower axial depths of cut and work your way up. Remember, it's a CNC machine. Consistent and reliable is the main goal. Double check your setup, work holding, and cam. Be confident and make sure you're wearing the proper safety equipment. And those butterflies you feel right before you hit the start button, that's the best.
Now let's open up the Vesc tool and look at the data log of the Makita router during that cut. Now this is where it gets really interesting because you see real life data and you can actually see what's going on when the machine is cutting. So this is the initial helix right here. And from what I heard in the video and from what I'm seeing as far as power usage, I can afford to push that a little bit higher, and I think that additional tool pressure would help with the cut. Once it gets into its main adaptive cuts, it's hitting around 275 to 300 watts. And it's funny because you can actually see the shape of the part in the graph. After it finishes the profile, it starts to do the bores, and that's why there's 4 different spikes here. The initial helix, and then it spikes when it starts to rough inside to out. Now let's look at the average power usage and compare it to what the millilizer estimated it to be. Looks to be around 280 watts, 275 watts, right? Open up the millilizer, estimated 282. That's spot on, and that definitely gives me confidence in all the other factors that it's predicting. There's also another interesting thing that I didn't actually see till I was done with the project. But if I would have cut in conventional cutting, I probably would have had a little bit smoother cut, and that's mainly due to just the high step over I was using, which was almost 100%. After the adapter was done, I used Scallop and a Datron 6mm single flute ball and mill for the semi-finish and finish tool paths. Once I finished those Scallop tool paths, I reinstalled a Datron 6mm 4-in-1 and ran an inside and outside contour to finish the surfaces and free the part.
This is the final part. The finish is right off the machine without any kind of post-processing or polishing. Now let's check the width. I didn't do any kind of fine-tuning in Fusion or any kind of step count adjustments in the machine controller. The width is supposed to be 3 inches. See how well we did. All within about a thou? That's good enough for me, especially for a belt-driven machine. Be safe, guys, be smart, and happy cutting.